The universe has long captivated us with the immense scale of space and time. In recent years, new giant telescopes have allowed us to look deeper into the universe than ever before. Astronomers believe that the stars and galaxies stretching to the limits of our vision may represent only a tiny fraction of everything that exists out there. They are pioneers of new theories describing a universe far beyond the boundaries of what we can see. Where does the universe end, and where do we exist within it? A remote outpost high in the Andes. Here, astronomers are opening an entirely new window into the universe. The Rubin Observatory, with its enormous state-of-the-art mirror, will send an immense stream of data to a global network of processing centers and supercomputers. Its targets are faint objects passing through our solar system, stars exploding within distant galaxies, or violent cosmic collisions. These bursts of energy, from the perspective of creation itself, are messages from a universe evolving in ways we can barely comprehend. They are pushing us into a new era of advanced scientific theories about the nature of time and space. Theories that challenge the philosophical assumptions that have guided humanity since ancient times. The Greeks were among the first to view natural events as subjects for human investigation rather than the unpredictable will of the gods. The philosopher and astronomer Anaxagoras proposed that meteorites were made from the same materials found on Earth and therefore may have originated from Earth itself. To the astronomers of that era, the world was composed of four primary elements: earth, water, air, and fire. The philosopher Aristotle believed that Earth was fundamentally different from the stars. He argued that stars are composed of an unchanging element known as the fifth element, or the cosmos. The realm of the stars, in Aristotle's view, was the home of the gods, arranged in a series of spherical layers surrounding the Earth. What would happen if a warrior reached the outermost sphere and threw a spear? Where would it go? Aristotle said it would not fly off on an infinite journey. Instead, it would move together with the stars inside a crystalline sphere surrounding the Earth. He believed that the universe, with Earth at its center, was limited in size. Aristotle fought fiercely to defend this view, a challenge that would one day transform science itself. Nearly 2 centuries earlier, the Greek mathematician Pythagoras and his followers had begun to see numerical relationships as the key to understanding the world around them. But while studying geometric forms, they discovered that some important ratios could not be expressed with simple numbers. One of the most important was the ratio between the circumference of a circle and its diameter, known as pi. Computer scientists have recently calculated pi to 5 trillion digits, confirming what the Greeks already knew. Pi is an infinite, non-repeating number. The discovery of irrational numbers such as pi caused such anxiety that one member of the Pythagorean school, Hippasus, was thrown into the sea for revealing their existence. To Aristotle, infinity represented the chaos from which the world itself had formed. In order to defend the idea that the universe had shape and limits, he developed a distinct philosophical view. On one hand, he pointed out that irrational numbers like pi generate another digit with every new calculation, yet can never reach a final number. Aristotle did not consider that value to be potentially infinite. In his view, what mattered more was that it was actually infinite. To understand this, take a ruler, divide it into smaller and smaller segments, and try to count the division points. Surely there must be a final number. Aristotle said, although we will never determine it. Aristotle defended the idea of the so-called first mover, the force that created the universe and set it into motion beyond human control. This idea later became the foundation for cosmological arguments about the origin and existence of God. A century later, Archimedes combined the concept of infinity with the measurement of curves and volumes. His method became known as the process of summation. Place an equilateral triangle inside a circle. Increase the number of sides to turn it into a square, then into a pentagon. As the number of sides approaches infinity, their total length becomes equal to the circumference of the circle. By dividing curves into infinitely many tiny segments, he was able to calculate curved lengths as well as areas and volumes. Thousands of years later, Archimedes' predictive methods were proven correct. Yet his ideas about infinity were not continued. Instead, Aristotle's view of a finite universe, with Earth fixed at the center, endured throughout the Christian era. However, not everyone shared that belief. Islamic scholars, Hindu thinkers, and even some Western philosophers proposed alternative views, including the idea that space itself was infinite. In Europe, the concept of a limited universe began to be questioned during the Renaissance. In 1543, the Polish astronomer Nicholas Copernicus argued that Earth revolved around the Sun, not the other way around. As a result, the ancient Greek celestial spheres began to collapse. When the astronomer Tycho Brahe discovered a supernova in 1572, followed later by a comet, these objects appeared to move independently from the stars. However, the Church opposed any view suggesting that the universe was infinite, because such an idea was seen as an intrusion upon the domain of God. But that did not stop a monk named Giordano Bruno. He traveled across Europe during the height of the Inquisition, proclaiming the existence of an infinite universe. He was burned alive in 1600. 9 years later, in 1609, Galileo Galilei used the first astronomical telescope to prove that the solar system and the universe were far larger than we had ever imagined. Galileo was later forced to recant his views. Yet the truth of a vastly greater universe had already begun to emerge. The poet John Milton wrote in Paradise Lost during the 17th century, "Amid the vastness of the universe, this earth is but a small speck, a grain of dust, or an atom." By the end of the 19th century, the mathematician George Cantor sought to remove metaphysics from mathematics. He became famous for combining finite and infinite numbers into a unified set theory, now considered one of the foundations of modern mathematics. To illustrate this idea, his followers proposed the example known as Hilbert's Hotel. You arrive at a hotel and discover it is completely full. But you are still lucky because the hotel contains an infinite number of rooms. The manager places you in room number 1, then moves the guest from room 1 into room 2, from room 2 into room 3, from room 3 into room 4, and so on. At first, the hotel contains one infinite set. After adding your room, it forms a new set, which is also infinite. Thus, there are now two infinite sets. One set is a subset of the other. The ability to work with infinite sets of different sizes allowed mathematicians to construct equations describing continuous motion and change over time. Even as mathematicians accepted the concept of infinity, scientists still struggled to reconcile it with the universe itself. Albert Einstein was among those who believed that if the universe had no limits, the night sky would be flooded with starlight from every direction, and we would experience infinite gravitational forces. Like Aristotle before him with his warrior and spear, Einstein believed the universe was curved by its own nature. Parallel lines would eventually meet, and beams of light would ultimately return to their point of origin. At that time, astronomers believed the universe had boundaries. It consisted of a flat disk of stars and galaxies, including the Milky Way and our solar system. That view collapsed in the 1920s. Edwin Hubble and Milton Humason used the 2.5-meter telescope at Mount Wilson Observatory in California to observe mysterious blurry patches in the sky known as nebulae. They discovered that some of these patches were actually galaxies, similar to the Milky Way, located at immense distances away. The farther away they were, the faster they moved away from us. This discovery became known as Hubble's law, and it led to the conclusion that the universe began at a special moment, a singular event known as the Big Bang. This idea rests on four major points. First, the universe is expanding in every direction. If you reverse the clock, you find that everything shares a common point of origin. Second, it provides a timeline for the formation of stars, galaxies, and the large-scale distribution of matter. Third, it creates a timeline for the chemical evolution of the universe, with light elements such as hydrogen dominating the early cosmos, while heavier elements formed over time through the birth and death of stars. Finally, it describes the universe in its primordial state immediately after the Big Bang. At that time, the universe was filled with an extremely hot cloud of gas that scattered all light. As the universe cooled and the first atoms formed, this cloud dissipated, allowing light to travel freely while space continued to expand. The spectral signature of that primordial light is observed today as the cosmic microwave background radiation. In one of the greatest accidental discoveries of all time, two physicists detected this ancient light during the 1960s. Arno Penzias and Robert Wilson were using a giant horn-shaped antenna that had originally been built as part of a long-distance radio transmission system. No matter where they pointed the instrument in the sky, they always detected an excess microwave signal. That noise, similar to the static once seen on old television screens, was the echo of the Big Bang itself. Decades later, scientists continued studying this signal with ever-increasing precision. The Hubble Space Telescope, launched into orbit on April 24, 1990, became one of the most important scientific milestones of our age. Just months earlier, the COBE satellite, Cosmic Background Explorer, had discovered that the microwave background radiation was not perfectly uniform. It contained a strange pattern of hot and cold spots. Later missions, especially Europe's Planck Observatory, mapped this structure with unprecedented detail. If scientists could determine the origin of those tiny fluctuations, they would not only understand how the universe began, but also why matter is distributed in the way we observe today. At the Large Hadron Collider, LHC, in Europe, scientists accelerate protons in opposite directions through a 27-kilometer circular tunnel. When these particles collide at nearly the speed of light, they create a fireball with temperatures exceeding 2 trillion degrees Celsius. That is roughly the temperature the universe reached within the first millionth of a second after its birth. These collisions produce an ultra-hot state of matter known as quark-gluon plasma. Scientists believe that in the early universe, a primordial energy field contained extremely tiny fluctuations. Those fluctuations generated pressure waves that propagated through the incredibly dense and hot matter of the young cosmos. As the universe expanded, these waves became the seeds for the formation of the largest structures in the universe. To test this idea, astronomers are constructing highly detailed three-dimensional maps of the cosmos. In the era of computer-controlled telescopes and automated observations, they can now survey vast portions of the sky. The Sloan Digital Sky Survey in New Mexico established the standard for large-scale cosmic mapping. Large metal plates were drilled with holes positioned precisely according to the coordinates of galaxies in the night sky. When optical fibers were inserted into those holes, the entire system became a tool capable of collecting light from hundreds of galaxies simultaneously. Each night, the system gathered light from hundreds of galaxies, recording information about their brightness and distance from Earth. From this enormous data set, astronomers constructed an entirely new three-dimensional map of the universe. Farther south, at observatories high in the mountains of Chile, new projects continue expanding our view of the cosmos. The Dark Energy Survey uses one of the largest cameras ever built, containing 62 high-resolution sensors. Each sensor can capture images of thousands of celestial objects across the observable universe, night after night, month after month. The system can observe a vast region covering nearly 1/4 of the southern sky, equivalent to about 1/8 of the entire sky visible from Earth. Meanwhile, the Rubin Observatory on a nearby mountaintop can survey nearly half the sky visible from Earth. But how far can we truly see into the depths of the universe? That limit is determined by the speed of light and the distance light has been able to travel since the Big Bang. Using the Hubble Space Telescope and other advanced astronomical instruments, astronomers have determined that the universe was born approximately 13.7 billion years ago. However, because space itself has expanded throughout that time, the radius of the observable universe today is not merely 13.7 billion light-years. It has expanded to roughly 46 billion light-years from Earth. If we look in opposite directions, the most distant galaxies we can currently observe are separated by about 92 billion light-years. And the observable horizons of those galaxies themselves extend even farther, to roughly 138 billion light-years from our position. So where does the universe end? In reality, the 92 billion light-year region of space that we can observe may be only a tiny speck within the entirety of the universe. That is the conclusion of a striking modern theory developed to answer two fundamental questions about the Big Bang. First, how could the universe become so enormous within such a tiny fraction of time? Second, why is it so astonishingly uniform? When observed on the largest scales, the density of galaxies appears nearly identical in every direction. That suggests whatever process created the universe must have occurred during the very first moments after its birth. A newer theory proposes that the universe was never truly empty. From the beginning, it was boiling with energy, where matter and antimatter were constantly being created and annihilated. In the 1980s, physicist Alan Guth proposed that a primordial energy field underwent an extremely rapid phase of expansion. According to his calculations, the entire universe could be about 10 to the 24 times larger than the observable universe. That is the number 1, followed by 24 zeros. In other words, comparing an atom to the observable universe would be similar to comparing the observable universe to the entirety of the cosmos. This explosive expansion phase helps explain why the universe is both immense and remarkably uniform. But it also opens the door to a far deeper possibility. Our universe may be only a small region inside something vastly larger, perhaps even infinite. For decades, astronomers noticed that the visible matter inside galaxies was not sufficient to generate the gravitational force required to hold them together. There must exist an invisible component whose true nature we still do not understand. Scientists call it dark matter. When dark matter is included in supercomputer simulations, researchers can successfully reproduce the enormous structures we observe throughout the universe today. Astronomers once wanted to know whether the gravity of dark matter was strong enough to slow down or even reverse the expansion of the universe. To find the answer, they studied special stellar explosions known as Type 1a supernovae. These explosions originate from white dwarf stars and possess nearly identical brightness throughout the universe. By comparing their apparent brightness, astronomers can precisely measure how fast the universe has expanded over time. The results were astonishing. The expansion of the universe was not slowing down, it was accelerating. The cause is believed to be a mysterious component known as dark energy. Today, dark energy accounts for roughly 3/4 of all matter and energy in the universe. If it has a nature similar to the primordial energy field that once drove cosmic inflation, then our universe may be only a small region inside a much larger reality. Some models even describe this greater structure as a fractal landscape where countless regions of space continuously generate new universes. In that picture, our universe becomes so small that it is almost impossible to imagine. There is also another possibility. Astronomers are using the Rubin Observatory and many other observatories to search for primordial black holes that may have formed shortly after the Big Bang. Some of them may have served as the seeds for the first galaxies. Over time, they could have grown into supermassive black holes with masses millions or even billions of times greater than the Sun. Smaller black holes may still be silently wandering through space among clouds of gas and stars. If one of these black holes passes in front of a distant star, the star's light would bend and briefly brighten. Detecting such objects could help us better understand the extreme conditions of the early universe. Some hypotheses even suggest that entirely new universes could be born from inside primordial black holes. Just over 500 years ago, during the time of Galileo, most people still believed the universe was simply a collection of stars surrounding the Earth. Today, we know that Earth is only a pale blue dot drifting through a universe filled with galaxies, galaxy clusters, colossal walls of matter, and enormous cosmic voids. These structures extend far beyond our observable horizon. And perhaps they continue forever. These discoveries raise a profound question. Do they make us smaller within the universe? Or is it our ability to understand and imagine the furthest limits of space and time that truly makes our existence extraordinary?